Okay, we are now streaming. Okay, I think since we are already 45 people, I think we can start. So let me give a few words of introduction. Thank you everybody for joining us. This seminar is part of the virtual seminars on complexity that is organized by the Center of Complexity and Biosystem of the University of Milan. And today, I have a great pleasure to have, we have a great pleasure to have Jim Sethna, who's professor at Cornell University, teaches physics and is a theoretical physicist who has many interests in many fields, from hard condensed matter to statistical physics, complex systems, applications to biophysics, systems biology, and data science. I would say it was probably it was doing data science before it was even called that name. So like understanding how to treat data and big data. So I cannot mention all his fundamental contributions to science that he did over the years. One important one that was the reason why we got in contact is the model for general model for phase transition in disordered systems and hysteresis. That was very inspiring. And but many other work, and we had the chance to collaborate on many of these topics, especially crackling noise, so the statistics of noise, and of a particular kind of noise. And today he will tell us about a very interesting idea that he has been working on for several years, the idea of sloppy models. So how do we do multi-parameters fit? So it started maybe from this question, so can we fit many parameters, and then it evolved in an entire story that has many ramifications and surprises every time. And just a few things before technical things before I give the floor to Jim. So this seminar is broadcast on YouTube, and you will find it later also a recording on YouTube. So after the seminar, we'll have a question and answer with the speaker. You can either type in the question on the chat and we can read it, or if you want, you can raise your hand and you can talk. And okay, so this is part of the series. Next speaker is still not determined, but hopefully will take place in May. We have one talk more or less every month. And you can find all the old talks in the YouTube channel of the Center for Complexity and Biosystem. Okay, without further ado, I leave the floor to Jim and his talk.
So thank you very much. I'm pleased to be here and share with you this work that was done with an enormous number of talented students and colleagues and friends. What I'm going to tell you about today is first about systems biology and other models with many parameters, and some what we thought was patterns of behavior, ill-conditioned models that have too many parameters to actually determine all of them from the experimental data, but yet we found that we could make predictions from these models. Then we'll go to our explanation of why so many models have this hierarchy of scales, how have this sloppiness where most parameter combinations don't matter. We'll explain using differential geometry and some interpolation theory. And then finally, I'll turn to some applications which may be useful for people who are interested in statistical mechanics and model visualization and model reduction. And in the meantime, I'm going to spend a little bit of time being a little grandiose. That there's this fundamental mystery of why science has been successful in understanding so much of our world. And in physics, we sort of have a handle on that. We've got small parameters. We've got separation of length scales and time scales and coarse graining and the normalization group. but those tools don't really extend to much of the rest of science. If you want to talk about psychology or most of biology, most of climate science, or at least parts of climate science, economics, all of these have successful theories. And I'd like to say that some of the reason that they're successful has to do with this sloppiness, with these hyperribbons in high dimensional spaces. And so I'd like to ground things in our physical world, where we have controlled approximations and small parameters. And there are two themes here. One is, well, first of all, high energy physics and condensed matter physics have different perspectives on this, but both of them basically have the same tools. In high energy physics, you have Schrodinger's equation, which is really annoyingly complicated, and you need lots and lots of details about different kinds of atoms and different kinds of nuclei and things to start with, and the calculations are messy. And then there are these more and more beautiful, more and more symmetrical field theories that there's a hierarchy of them, where each one of them can, at low energies, produce an effective theory and as you go up this hierarchy, you get fewer and fewer parameters. So this is a reductionist approach where we explain Schrodinger's equation in terms of more beautiful, more elegant theories. In condensed matter, we have Schrodinger's equation, which we consider horrible, nasty chemistry kind of stuff. And then the physicists have theories that branch out from that on lower energy scales, where we have spontaneous symmetry breaking, leading to beautiful, elegant theories of superconductors and magnets and metals and liquid crystals. And there are two things that physicists, a very severe caricature, there are two kinds of things that physicists do. One is to derive new theories from others. And the other one is to guess new theories where we have no idea what's going on. That and it's those two themes that will manifest themselves in our analysis, not of physical models where we can hope to have a direct connection between scales, but in much more general situations where and then the other question is, what does it mean to understand a system which is fundamentally and microscopically really complicated? And developing a predictive, simple model from a complicated system is part of what physicists love to do. The first branch, parameters. Oh, by the way, I want to say and emphasize that I like questions. If too many questions start coming up, I'll say, no, we should move on and continue. But having an entire talk where everyone is sitting there passively trying to keep awake is not much fun. It's much more fun to have people interrupting and probing questions. It's always the best. Any questions so far? Okay, we got into this by a crowd of students who wanted to do systems biology. This was before systems biology was called systems biology. It was prompted by students who were convinced that they could, understand cancer somehow by applying science, physics to all this data that our friends were. And we had a cancer biologist And the cancer biologist very patiently, and I very patiently listened to the students with their ideas about, oh, apoptosis and this and that. And he said, look, let's take a tangible model. This is Rick Serione, and he wrote this model down. And he said, this is a model of signal transduction from the membrane to the nucleus, and and one pathway leads to cell reproduction, and the other pathway leads to cells differentiating into neuron-like objects. And he said, this is well studied, everyone understands it. And he drew this diagram. And I said, what is that diagram? We can't deal with arrows and things. And he said, oh, no, there are some differential equations. And he wrote down these differential equations, roughly speaking. And he said, I can't get any of my biology people to think about these differential equations because they don't like math. And we said, we could type them in, but it wouldn't work. You have 48 parameters. So here's one of these equations, which you otherwise can't read. It's a nonlinear differential equation. It's basically chemistry equations, except they simplify them by removing some unnecessary parameters, which we'll talk more about. And you end up with 6 parameters in this nonlinear differential equation. And this is just one equation among a very large number of them. And there are a total of 48 parameters. And I said, 48 parameters, we can fit anything with 48 parameters. And I was completely wrong. But I also said you'd never be able to figure out those 48 parameters. And I was right about that. Okay, so 48 parameter fit to data. This was the kind of data you get. That you remember there were 2 growth factors, hormones that were attaching at the top. And one of them produces up and down, the other one produces up and stationary, and there were 48 parameters, and here's the uncertainty of each parameter. This is the fractional uncertainty. So the best known parameter can be determined with a 5,000% error. Okay. So I was right. You couldn't determine the parameters. And now, what about predictions? Well, we took a possible experiment exposing things to a drug LY, which would turn off one of the pathways, and we actually got a prediction that nothing would happen. Our cancer biologist expert suggested that that drug will be effective at changing this transient behavior to sustained behavior, and that didn't happen. And our prediction happened to be right, but you can't publish something saying, well, we made a prediction that worked, even though Rick Serione said it wouldn't. What was exciting here was not that we made the right prediction, it's that we could make a prediction at all, given that all our parameters were off by a factor of 50 or 500,000. So when I say there was a prediction, this is the 1 sigma error bar. You take the existing experimental data and you fit it with least squares, and you can estimate error bars, and these error bars are enormous and these error bars are small. And the reason was a remarkable sloppiness in the fit, that there were a few stiff combinations of parameters. So here's a contour plot. And if you move in this direction, the parameter changes, which are a combination of microscopic parameters, matter a lot. And if you move in this particular combination of parameters, they matter very little. We call these stiff directions and these sloppy directions. And you'll see that there are a lot more sloppy directions than stiff directions. The other thing I should point out is the axes of these two, this axis and this axis are off by a factor of 1,000. So to make this plot the two axes equivalent, I would need to stretch it by a factor of 1,000 in the horizontal direction. So this is a really striking range of sloppinesses. This is not news. Ill-conditioned problems have been around for a long time. Where some parameter directions matter a lot more than others. But I will show you in a moment why we thought that there had to be some sort of more beautiful explanation than just, oh, you've got some parameters you can't measure. One thing I wanted to mention, this form, this formula here for the cost, if you take its second derivative with respect to the parameters, that's how you get these ellipsoids. That cost is going to become our metric tensor when we start doing differential geometry. And the eigenvalues of that metric tensor, the eigenvalues of the cost Hessian, span an enormous range. So I showed you that some parameters are millions of times less well determined than others. This is the eigenvalues of those ellipsoid, and you can see that the eigenvalues are spread over 6 orders of magnitude for all of these different models. This was the model that we just showed. This is fitting exponentials to data. This is the quantum wave functions used in quantum Monte Carlo, one of the most accurate ways of doing quantum chemistry calculations. This is the cosmic microwave background, which I'll talk about later. Ising model, diffusion, meat oxidation accelerators, neural networks, a Van der Pol oscillator, circadian clock rhythms, interatomic potentials, power systems, Huxley models. All of these models show roughly equal spacing of the eigenvalues of the cost Hessian. Obviously, they're not exactly equally spaced. It looks a lot like random matrix theory. We've never been able to figure out a tie to random matrix theory. But I will try to spend much of the rest of the talk explaining why this happens. Now, the cost Hessian is not, it's a least squares problem. And there are lots of problems in physics in which you don't have predictions that are, data points with least squares. Much of statistical mechanics generates probability distributions, and you can generalize this cost Hessian metric into what's called the Fisher information matrix or Fisher information metric, which has this rather obscure formula, second derivative of the log of the probability with respect to parameters, which agrees with the cost Hessian I was telling you about before, if you have a least squares model. And when I talk about problems like the Ising model and the cosmic microwave background, I'll be using this definition of the metric instead of the instead of the least squares metric. Okay, should I pause just a moment before any questions?
Yes, I have a question if I can. Your cost function is quite system dependent, isn't it? I mean, you have a different cost function for every system that you, whose eigenvalues you have shown. Is it correct? Yes. So yes. You have kind of an arbitrary choice in that. I mean, you are comparing things.
Even within a given biological system, you can have different cost functions with different experimental predictions.
Yeah.
That you could measure different things in the same system. And it's clearly true that you could do a set of experiments for which it wouldn't be sloppy. They would be doing things like measuring each of the parameters separately. That would not be sloppy. But it turns out that that's, I asked my experimental colleague, why don't you just measure the parameters? And he said he couldn't pay people enough to measure those parameters. It's too boring and they never get another job. The biologists don't want to know what the parameters are because they know they're useless. So it's clear that the sloppiness has something to do with how you pick the experiments. And it's clear that what we mean by understanding is thinking about things on a scale where things stop being complicated, where all the parameters don't matter separately. So this is, again, tied in with this idea of emergence, that we're looking for a comprehensible world, and getting too stuck in the weeds by trying to measure all the parameters it's illuminating how we naturally choose collective behavior. Now I can say one more thing. If you take one of these models and instead of taking the experiments that have been done, we tried taking all possible experiments predicted by our model. So we would take continuous data of all possible parameters and move the experimental conditions around in some complicated way, and we got the same cost estimate. It was, of course, shifted up and down, but all those eigenvalues and all those eigenvectors were basically the same. It's amazingly robust. So on the one hand, you're right, different data will lead to different sloppinesses, but you have to go to really strange experiments to really change the model manifolds, to change the structure.
Thank you.
Excellent question. Other questions? Okay, so let me make a contact. In physics, there are two major tools for getting emergent behavior. One is the continuum limit that was sort of the 19th century, where you would find equations for waves on strings and hydrodynamics and things like that by taking the microscopic theory and coarse graining it until it looked like a continuum, or drawing free body diagrams and things like that. So the diffusion equation is an example of that. We studied the diffusion equation in this context. The other method was developed around 1970 by Leo Kadanoff and Ken Wilson and Michael Fisher, which is the renormalization group. And the prototype example of that is the Ising model. And both of those systems, if you look at them microscopically, they're basically not sloppy. If you take every spin configuration and its probability and take the Fisher information metric and look at it, the eigenvalues are spread over 4 orders of magnitude or 5 orders of magnitude, but really, basically, they're not very sloppy. If you coarse grain, as Ken Wilson suggested, but without this apparatus of developing effective Hamiltonians on different scales, just take the Fisher information metric for the coarse grain model, you discover that sloppiness emerges. In fact, the stiff directions are the parameter combinations that govern the shift in TC and the external field, and the irrelevant directions, the least irrelevant and the next most irrelevant, all fall into different degrees of coarsening. So roughly speaking, we can't tell you what the effective Hamiltonians are. We can't tell you about universal scaling functions, but just by thinking about the Fisher information metric and how it changes under coarse graining, we can reproduce many of the key concepts in coarse graining and renormalization group. You explain why things become simpler. It doesn't give you the tools to generate the simpler theory. Okay, now it's my responsibility to try to explain why sloppiness arises in fields other than physics. Ooh. Huh. That's never happened before. I've lost my plot here. Imagine that there's a contour plot here where I have ellipsoids for a very simple model fit to data, where my model at time t sub n is a sum of two exponentials, one with parameter theta 1, one with parameter theta 2. And I'm going to take the model manifold where I take 3 data points. So t sub n, thetas are my parameters, and t sub n are my control variables. And for each possible time, I get a different dimension on a manifold of predictions. So this is a 3-dimensional manifold giving the predictions y1, y2, y3 at times t1, t2, and t3. Now, whoop, technical difficulties. Notice a few things about this manifold. It's curved. This is a nonlinear model. The parameters, theta 1 and theta 2, are coordinates on this model manifold. For every pair of parameters, I get a point in the model manifold. The model manifold has a natural metric, which is the least squares distance between the given data point and the prediction of the model, y sub n and d sub n. The sum of the squares gives you the distance. So the metric on the manifold is inherited from the space. Two other things. One thing is this model manifold does not extend to infinity. If I take theta 1 to be 0 or infinity, I don't get an infinite answer. I just get either a time-independent component of the prediction if I take one of the parameters to 0, or I get a time infinitely sharp time dependence where the contribution at 0 becomes 1, at later times becomes 0. And so I get a model boundary at theta 0, theta is infinity, or when the two parameters are equal, because for this particular model, the model manifold, which is sort of an image of a square region, gets folded in half. Those boundaries are going to be important for model reduction later, because we want to find simpler models with fewer free parameters. And this is an example of the boundaries of the model become simpler models. Finally,
sorry.
Yep.
Why is there a boundary at theta equals 0? What is if your data is increasing?
For radioactive decay, theta less than 0 doesn't make any sense. I'm thinking of this as a model of radioactivity.
Okay.
Finally, one final thing that's going to be important is suppose I took a measurement at time t2 and I fit the model to that measurement. That would restrict the values of theta 1 and theta 2 to be ones that predicted that value at t2. And that would correspond to a cut along y2 as a constant on this model manifold, and my reduced model fit to one data point would be a dimension, a model of one less dimension where I slice in one direction. Now, all I have to do from here on is to think about the geometry of these models, not in two-dimensional models, but in models with like 48 parameters, and I'll be great. When you have more parameters, you discover these model manifolds become a particularly funny geometry in high dimensional space. We call them hyperribbons. That just like we had some a few stiff directions and many sloppy directions in parameter space, so I will get some long directions and many thin directions on the model manifold. So if I take a sloppy direction, say the 7th sloppiest direction, and I move in a geodesic along that direction in data space, you can imagine, because it's sloppy, you can move a long distance in parameter space along that direction without changing the behavior. And sure enough, the sloppy directions, you can go all the way to infinity on a geodesic and have a width that's rather small. And the stiff directions are the long directions. So this isn't actually the whole model manifold. This is a two-dimensional cut of a model manifold. And after you slice it twice, you get this very thin, so like a ribbon. It's got a long direction, a much smaller width, and a very thin thickness. And we find that's true very generally for all of these models. So I've reduced the problem of eigenvalues at one point on this model manifold, on the metric tensor at one point, to a geometry problem of the manifold of all possible predictions. At this point, it took us a long time to go from that to real math, but we now have rigorous hyperellipsoid bounds on the model manifold. So the model manifold, I said, was longer than wide and wider than thickness and hierarchically thinner and thinner. And now I'm going to explain briefly the physics behind a mathematical theorem that we have that shows that the entire model manifold, given smoothness approximations for the predictions, and given what data points, what time points you measure for a model, what experimental conditions your control variables are exploring, you can get explicit bounds on the widths of the model manifold. And the argument runs like this. You remember I was saying before that you needed, if you take a point and fit it and look at the predictions after one data point is fit, it restricts the possible behaviors to a slice of the model manifold. And you can imagine that if you slice a hyperribbon in a typical direction, a hyperribbon is much longer than it is wide. When you slice it, will basically become a hyperribbon that's much wider than it is thick, but the length has gone away. And so each data point slices the model manifold, and the model manifold is a hyperribbon if each of those slices seriously reduces the width in other directions. Now, if I think of a simple model, which is just predicting the time points with only one parameter, which will be time here. So imagine some kind of reaction as a function of time, and I'm only measuring one thing. Then the the entire range of behaviors is controlled by a theorem of interpolation theory. That if you have a function y of t, and it's then the after you fit 4 data points, the range of possible behaviors is given by the maximum value of the 4th derivative divided by 4 factorial, which, if you think of a Taylor series for y, is just the radius of convergence to the nth, 1 over the radius of convergence to the nth power. So each slice, each time you take a data point, if you took another data point here, all of these predictions would get more precise. And the precision that you can expect is given by how big or how small the nth derivative is for the family of models you have. So this gives us a hierarchy. These ranges are the widths of the model manifold at time c, at time t. These are the possible ranges of behavior. And it's interesting, if you pick a model from physics and from chemistry and from population biology, you can simultaneously bound all of them with the same hyperellipsoid, because all that matters is how smooth they are and how many and what data points you're exploring them at. And you can find all of the widths of the model manifold. So that's the black dots. Sorry. So the 3 colors are the widths of the model manifold, and then the black dots are an explicit bound, and the dashed line is one of our rigorous bounds on the explicit bound on the data. And you can see now we've explained why you get power law decays. There are lots of other reasons why you get ill-conditioned models. You can have combinations of parameters that algebraically don't matter, that you've got more parameters than you need in your experiment. You can have separation of time scales. You can have separation of length scales. Those are not part of this. In fact, they will tend to make things even sloppier. This happens in the absence of any of those, and just has to do with the fact that you've got more data points, more than 1 data point per radius of convergence. As soon as you have enough data to basically constrain your family of models, it'll start happening. Let me pause now before I leap into my 2 statistical mechanics applications and ask for more questions. No?
So maybe,
Okay.
Maybe I have one question. I've seen that there is no negative eigenvalue in the systems. This means that all the systems are in equilibrium. So what happens if, for example, the cases you were mentioning of more complex phenomena are basically related to this non-equilibrium phenomena? This is the reason?
So the word equilibrium isn't right. That the thing I'm taking eigenvalues of is a distance function.
Okay.
So if I have a good fit, my distance is small. If I have a bad fit, my distance is big. But I just wanted to say, the lack of negative eigenvalues will come up in just a moment. but in a very bizarre way. So I'm glad you asked the question, because it introduces a very interesting statement about model manifolds that I'm going to talk about in just a moment.
Okay, thank you.
Other questions? Okay, so I'm going to start off by giving you a way of looking at more complicated models, and as I was talking to Silvia Bonfanti, I'm going to give you hyperribbons in the Minkowski space for those models, and then I'm going to talk about not my work but Mark Transtrum's work, where he uses these methods to do model reduction, to give you simpler models that are more comprehensible to ordinary humans in a systematic way using the differential geometry of model manifolds. So Catherine Quinn was looking at, let me actually do this in a slightly different order. Catherine Quinn was looking at the models of the cosmic microwave background radiation. These are lambda CDM models. Lambda cold dark matter. They have dark matter and dark energy and Hubble constants and as their parameters. And I said, why don't we make a model manifold for the space of all possible universes and see if it's sloppy? And this was much more challenging than I expected. That I started by saying, why don't you just take the correlation function, angle correlation function that everyone plots? And she said that wasn't isometric. That is, it's a vector, a prediction of the model, but that prediction as a image of the model manifold didn't have the Fisher information metric as the distance function. And then we started thinking about probability distributions in general. And it turns out that you have a nice way of embedding probabilistic models in high dimensional spaces, which is to take the probability distribution P of theta for each different spin configuration for an Ising model or each different pattern of microwave background radiation, and take its square root. So the sum of the squares of the square root of the probability distribution is 1. So it gives you a point on the unit sphere. And that turns out to give an isometric embedding. And we tried it for the universes, and we got a horrible dust pattern. That it was a huge dimensional space. It did not give a low dimensional embedding. And Catherine was explaining to me that there was too much data. That if she did only a few spherical harmonics, she got a picture. But if she did more and more spherical harmonics, it got worse and worse. And it dawned on us that the formulas are simple enough that we could take the limit of 0 data. We could use all the data and take the limit and think of replica theory. We could use all the data and think of taking 1 snapshot and 2 snapshots and 3 snapshots of the universe. Explain what the embedding would look like on the model manifold in probability space for those higher and higher, and then take the limit of the number of snapshots going to 0. That replica theory trick worked and gave a very nice embedding. And so here's an example. Here's the 2x2 Ising model. Here's the 4x4 Ising model. Here's 4 replicas of the 2x2 Ising model. And here's what you would expect if you had a 128 by 128 Ising model. but instead we're taking a large number of 2x2 Ising models. And you can see that this looks like dust, and that's because almost all of the data points are sitting in near the origin and long distances in other directions in parameter space. And then here's the replica theory limit. So this would be the local model manifold for the Ising model in this limit. Now, one thing I should say is that it does a nice job of things like model manifolds for learning digits by neural networks. And the other thing I should say is that this final model manifold, let me go on to the next page. Here's the universes, here's the digits. This model manifold is partly, is not embedded in Euclidean space, that some of the eigenvalues that you take the limit n goes to 0 become negative. And so this becomes embedding in Minkowski space. Now, so when you look at distances between points, your eye thinks that all of these coordinates are equivalent, but some of them actually, a distance in some directions lowers the distance between points. And then later on, look, nature is sometimes really cooperative. It wants you to be able to do things that you want to do. And somebody mentioned in the seminar that we ended up with something called the Bhattacharya divergence as our fundamental thing after replica theory and taking the limit of zero data. And they said, what would happen if you used the Kolbach-Liebler divergence? It turns out the same technique applied to the Kolbach-Liebler divergence gives you a isometric embedding in a finite dimensional space. So all of those plots I showed you before, talking about, is this model a hyperribbon? Is this model a hyperribbon? Hyperribbon was something that got thinner and thinner as you went to higher and higher dimensions. The the Ising model is in 4 dimensions, not an infinite number of dimensions, just 4. And so it gets thinner and thinner as you go higher and higher dimensions. But after the 4th dimension, it becomes infinitely thin. And this becomes, you get explicit formulas for the positions in the model manifold for any of what's called an exponential family in probability distributions. You can find finite dimensional embeddings. It's fascinating. Now, finally, I want to answer a question that many times I'm asked in seminars, that if my systems biology model has all of these sloppy directions, has all these parameter combinations that are unnecessary, why don't I make a coarse-grained model? Why don't I just simplify it? And I had all kinds of complicated arguments that actually the sloppy eigendirections are linear, have lots of non-zero eigendirections, and it was hard to tell which parameter to remove. And you didn't want to remove parameters because the biologists actually cared about all those parameters. And then Mark Transtrum solved the problem in the most elegant possible way. So Mark's method was to say, he was taking geodesics to find widths of model manifolds. And when he discovered that as he went close to the edge, which is moving towards infinity in parameter space, right? How do you know when to quit? Well, he could figure that out by looking at the eigenvalues, that 2 of the eigenvalues would get really, really big and all the other directions would get small. So this is This is the direction that he's moving along this geodesic. And he's moving in a direction that changes two eigenvalues and none of the others. And you can think of that as this parameter is getting bigger and this parameter is getting smaller, like the forward and backward reaction rates. If you take the log of the forward and backward reaction rates, and they're moving equally rapidly to infinity, then or maybe they're both going to plus infinity, that would just say that this reaction is in local equilibrium, and you can just remove the two reaction rates and get a simpler problem. And he would do that over and over again, and he would removing one parameter at a time, he would get a simpler model. And so you remember this original model with the 48 parameters and 29 ODEs and complicated diagram that you didn't understand. And we could, if you were Rick Sirione, you could tell a story, you know, feedback loops and forward and two different side branches. And then Mark applied his method. Oh, there is the coarse-grained model that Rick Sirione described to us, except it's missing one branch that turned out not to be useful. So there's one branch here that keeps there's a central pathway that communicates a signal. Here's one that supplements it, that keeps it going. Here's a negative feedback loop. This happened automatically. He did not hand tune anything. He took the sloppiest direction, went to the boundary of the model manifold, removed one parameter, repeated the process 36 times, and got a 12 parameter model. The 12 parameter model, the ODEs are much simpler looking. And it's not sloppy. And each of these parameters, here's theta 9, here's an example. It's an explicit formula of the original parameters. This does not make this the correct model. But this model fits all known data equally well as the complicated model and is comprehensible. You can still test it to see if it's correct by doing new experiments. But the idea of saying, oh, I'm going to do an experiment to measure this parameter, and if your fit is wrong, then your model is wrong, that's just silly, because nobody knows the parameters. But if you say, I can fundamentally test whether there's a feedback loop here, that's something that a biological, a new Nature paper, there are new Nature papers on these, Nature and Science papers on this particular system. They were coming out like 2 a year ever since we wrote our paper. And each of them would say, I've got a new protein that's important for this cycle. And my argument would be, depends on what you want in terms of understanding the biology. But at some level, this is the prediction that you're getting out of your model, not this. So to end, I'd like to talk a little, before we go into big questions, any questions? Sorry. Any questions about this? Here's my chance to be grandiose. Having a low dimensional model gives us the ability to think about a problem that's too complicated otherwise. It gives us insights. You can think of almost like superstitions and ancient human abilities to try to figure out the world around them by building structures that seem to work for them, are making use of the sloppiness of the world. Engineers take physics and then they extend it by throwing new things in that they need to describe their world. So if you look at the theory of plastic flow in metals, which I've done a lot of study of, along with Stefano, a lot of the engineers have very effective tools where they say, well, we're going to throw in a damage, and we're going to measure the properties, and we're going to figure out how the damage affects the yield strength and the fracture toughness, and they'll fit data, and they'll make up a model, and you can imagine how complicated the microscopic stuff that's going on in there, and how simple the model is that describes it. And it's relying somehow on the sloppiness, on the fact that there's a low dimensional space of behaviors, and any model that can capture that low dimensional structure will give you predictions. We spent some time thinking about algorithms for doing things, not only model reduction, but also how to just fit a model with least squares. Improvements on Levenberg-Marquardt algorithms. There are biological implications. There are all these neutral spaces that people talk about in biology, and the fact that it's not only true that certain swappings of proteins or swappings of labels in the RNA are neutral spaces, but there are large numbers of neutral spaces in the chemotype, in the ways in which reactions occur inside the cell that don't affect the phenotype because of sloppiness. Machine learning, you think that 48 parameters is ridiculous, and most systems biology models these days have hundreds of parameters or thousands. Machine learning has millions of parameters. You just throw them in. You think that they would have problems with overfitting and things like that, but it's a nonlinear model, and they're very sloppy. And you can look at the stiffnesses and try to understand what it is about the nature of the things they're trying to learn that's low dimensional that makes this work. Not low dimensional meaning 4-dimensional anymore. The space of pictures on the internet is not described by a 4-dimensional space, but low dimensional compared to the millions of parameters in the model. And just the concept of why the world is comprehensible, I think it's a really deep question. Thank you very much.
Thanks a lot for the nice talk, and of course, with many implications for many fields. So I wonder if there are questions. More questions? Yes, Isabella, you can ask your question.
Yeah, hi. I was wondering basically where these negative eigenvalues come from. So in a sense, I guess, like for the Minkowski embedding, because in a sense, I guess, I thought that like if you have like Fisher information matrices, or that it depends on covariance matrices in a sense, and that these are usually positive definite. And
exactly. They were positive definite for 1, 2, 3, 4, 5 copies. But if you take the limit of 0 copies, they stop being positive definite.
Ah, okay.
And you can argue that if you don't violate that, you can't have a low dimensional embedding. That you can make a clean argument that any embedding in a Euclidean space will fail because of the triangle inequality, basically. That if I have 4 models, each of which is orthogonal to the others, which is easy to do. I just take 4 Gaussians and space them several sigma apart, then they will form an equilateral tetrahedron, and I'll need at least 3 dimensions to embed it. And that so you're doomed in Euclidean space. But because because the triangle inequality no longer applies in Minkowski space, those four models can be stretched out into a nice straight line, and I can have an infinite number of models, each of which is orthogonal to one another, and how orthogonal they are starts to matter. How many sigma apart they are becomes relevant, and that's how the Minkowski embedding works. But you're absolutely right. It's a correlation matrix or covariance matrix, I've forgotten which, that determines the Fisher information metric, and that's positive in any physical statement. But replica theory often gives you strange things when you take the limit, and that's what it gave us.
Okay, good. Thanks.
Guido, please.
Yes. In order to apply what you have just told us, you have to solve exactly the model in order to get the eigenvalues and so on, and to find what are the sloppy directions.
I'm not sure what you mean by solve exactly. Some of these models are pretty simple, like, you know, we solve the differential equations, and so then taking derivatives. The Ising model, which we did here, this is a 1.8 by 1.8 Ising model. You cannot solve analytically, you know, to find the whole probability distribution. But it turned out, because nature is kind, that you can do this with Monte Carlo. All you have to do is estimate the magnetization and the internal energy, and you can get the coordinates here. So on the one hand, so I should be asking, what kind of model are you thinking about when you say you want to be able to apply this to something you can't solve completely?
Well, any model like, I was thinking, for example, a spin glass, in which the dependence on the parameter is awful.
So one of my students spent a long time doing this for the spin glass, and he had first used Alan Middleton's method of computing exact free energies for particular spin glasses, and got a long ways with that, and then ended up just estimating things using Monte Carlo simulations. But he could only do, you know, 20 by 20 spin glasses, or 20 spin glass. I've forgotten what it was. It was small spin glass.
Okay.
So sometimes there are problems, and sometimes there are problems where you want to take the thermodynamic limit and you have disorder and you want to have model simplification. I'm not sure I have an answer in general, but it was surprising that once we decided this is what we wanted for things like the Ising model, which we thought we couldn't solve, this is 4x4 Ising model is the biggest one we could do exactly. Then we found another trick that made it possible to do. And if you're interested in the application of spin glasses, you should read Colin Clement's PhD thesis, because we spent a long time studying that, and we ended up not getting anything that we felt was publishable. So I encourage you to take a look at it and see if it inspires you to do something slightly different, because a lot of things are fun and a lot of technical challenges he solved.
Okay, more questions? I don't see any raised hand. But of course, we had also questions during the talk.
You can also just barge in.
Yeah, exactly. So,
This has been great fun.
Thanks a lot. Thanks, and we'd like to give an applause to Jim and for the nice talk. Virtual applause. And okay, thanks a lot. There is somebody. Oh, a question in the chat.
No.
Why are the eigenvalues spaced evenly in log space?
Our fundamental answer is that we have a bound on the eigenvalues that dies evenly on the log space, and it appears that that bound is pretty good. I was very pleased to get that answer. That was very cool. That you can actually, so it turns out that you can bound things using a Vandermonde determinant for polynomial approximations, and you can apply that even though these are not polynomial models because of interpolation theory. And then the Vandermonde matrix has the properties that you can solve to find that its singular values are bounded above by a power law distribution, just like that. So that's a telegraphic way of saying it. And, now, a more physical answer, I guess, is that every time you take another measurement, you get a new bound where this quantity goes like 1 over r to the n, where the r is the radius of convergence. So if you have an analytic model whose time dependence has a radius of convergence, and then these data points get closer together by 1 more factor of the difference in time. So if your total range of times is fixed and you add more data points, then this looks like a delta t divided by r, and every time you take a new data point, you get another power. So that gives you a hierarchical bound on the width of the model manifold. So this is a beautiful question. I'm glad you asked it, whoever it was.
Okay. So if there are no other questions, I think we thank Jim again for his nice, entertaining seminar, and we hope to see you soon.
Next time.
Yeah, sounds good.
Thanks everybody for joining and for asking questions.